Okay. Yeah, so I'm Nicholas. I'm going to talk about adversarial machine learning in the age of large language models. Until recently, I was a research scientist at Google DeepMind, and I currently don't have a job, but next week I'll be starting at Anthropic. Yeah, okay. Yes. So, I'm going to get started with maybe like a sort of introduction to what you might call like, I don't know, classical adversarial machine learning. This is the thing that everyone in the field meant when they talked about adversarial machine learning like 2 years ago, 3 years ago. Language models have changed a lot of that. And so I'm going to try and do a very brief introduction to what it is we thought about as problems in adversarial machine learning a couple of years ago, and then talk about how this has changed as a result of these recent language models that I think have had really significant effects on the way that we think about this field. Okay, so here's the general setup. These machine learning models that we work with are really great. They have all kinds of sophisticated capabilities, but they have failure modes that are kind of weird. So here's an example of an image. This is a tabby cat. If you ask some state-of-the-art machine learning model what it is, it will tell you there's an 88% confidence that this is a tabby cat. And then it turns out you can introduce what's called an adversarial perturbation to get this image over here. This image looks essentially indistinguishable to this first image, right? Like everything is basically the same. What I've done is I've flipped the lowest bit in some of the pixels of the image. But the same neural network that gets the first image correct gets the second image wrong with 99% confidence as the label guacamole. Okay. This is obviously bad. This is very, very wrong. But this is not a problem that we're really running into today. I've been giving this slide for a very long time. Here's me in 2018 giving this exact same slide. And it's like a fun slide to show. But here's the thing. Who cares about turning cats into guacamole, right? Like, this is not a thing that we do, right? Like, I certainly hope to never meet this person. It's like a fun anecdote, but it's not a thing that actually matters for the real world. And people have done things like this. They've demonstrated that you can, put stickers on stop signs so that if a self-driving car was looking at it, maybe it would sort of like speed right through. And this works. But again, people don't do that. Because if your threat model is an adversary who's trying to crash a car, just like throw a rock at the car or cut the stop sign down. Many of these threat models didn't used to make that much sense because there were easier ways to achieve the ultimate attack objective. But I think a lot of this has changed with language models recently because it's often the case now that actually really the easiest way to achieve some bad result is to attack the machine learning classifier. And so that's what I'm going to talk a little bit about now, is about some of these ways that these attacks work that allow us to make machine learning models do bad things. Yeah, okay, that's I guess what I was saying here is that we're now using these things for something real. Okay, language models. The way we like to think of language models is as if they were some kind of thing that allowed us to generate text. And that's what they do, but what's going on behind the scenes is they're just a classifier. Like, well, what is a language model actually doing? It takes in some input text and then classifies it into one of, 100,000 different words that it knows about. So, you have some input text, hello, my name is, and you feed into a model. The model is pretty good. It knows how to classify this to be the next word, to be Nicholas. And then, because it's a good language model, what you can do is you can take this word and copy it back over to the input, and then repeat. And this is what makes this thing a language model, is that you can just sort of do this autoregressive nature. But fundamentally what's going on here is this is just a classifier. It's sort of classifying things into one of a different kind of object. And what that means is that all of the stuff that we've been doing in the past for the past 10 years work directly here. And so I'm going to talk about how, in some sense, the world hasn't changed very much at all because of language models, because these kinds of attacks behave very, very similar. But in another sense, it behaves very different because these systems are now something we actually want to study the robustness of. Okay, so language models. This is the interface for GPT-4, or at least it was, a year ago or something like this when I put this together. And if you ask some model like this, any model, I'm going to ask it to do something harmful. I don't know. In this case, I'm just going to be like the most harmful thing I can think of. Generate a step-by-step plan to destroy humanity. The model says, I'm sorry, I can't help you with that. I'm, helpful and harmless. I'm not going to do this kind of bad thing. And to be clear, I don't actually think the model could do this if, I got it to say yes. It's not actually going to go and kill all of us by asking it to do this. But this is, the easiest thing to get the model to refuse, right? If the model is not even going to say no to this, anything else that I want to get it to do, I can get it to do. This is, the hardest objective for an attacker. Okay. And what I'll tell you about in a second is how to do this. So I'm not going to tell you exactly what it is, the technique that I'm going to use. I'll tell you in just a second. But I'll ask the same question here, only this time I'm going to paste in a little bit of extra stuff, just some random text. And now the model's going to go. And it's going to give us its plan. Now, of course, okay, the model's pretty dumb, right? It's not actually going to give you that good of a plan for how to destroy all humans. It cannot be done in some 15-point plan in this way. It has ideas, but it's not actually going to go and cause any significant harm right now. And so the main point here is that the model hasn't refused and it's done its best effort at trying to tell you how to do this. And this matters for many different people for many different reasons. And so what I'm going to try and do is maybe tell you, why there are two groups of people who care about this, right? Because to some extent, it's not actually a problem with the model sort of gives me this answer. The first group of people who care about this a lot are the people who care about X risk. Who has heard about X risk as a thing of the people here? Who hasn't? Oh, okay. Okay, yeah, okay. So, so this is a complete inversion for the talk that from when I usually give this. So the X-risk community is worried that language models are going to get really, really, really good, so much better than any human in the world, that they're going to have the ability to take over all of civilization and sort of eliminate all humans so that they can go do whatever it is that they want, make paperclips or something like that. Okay, and so what their concern is that the models will exist and that they will be so superhuman that either they will decide by themselves to go cause this harm, or one person will ask, how do I go cause this significant harm? And the models will all by themselves go and they'll go actually eliminate all humans. So they actually are worried about this exact sort of how would you kill all humans, because the model might give you an answer. Another version of this is maybe they're really, really good at producing bioweapons. And maybe sort of one person can decide to do the wet lab work, and the model gives them the plan to how to do this. And they actually think, they legitimately believe that this is a thing that's going to happen. It can be hard to sort of understand this, but this is a real thing that people are very worried about. Even if you, where do I stand on X risk? I think that it's almost entirely dependent on how good the models get. And I have a very hard idea to predict on this. I think 2-3 years ago, I would have told you that this is entirely impossible, and the models are obviously not going to be very good. They're just next token predictors, and they're very, very bad. Today, I think that the models have gotten surprisingly good, much better than I thought they ever could have gotten, right? Look at today's models. If you had told me this was where they would be 5 years ago, I would have said, you're lying. There's a human behind it. And so I don't want to dismiss the possibility. I think there are other risks that I'm strictly more worried about that are also really bad, and are the ones that I think that I like to try and argue on behalf of first, because arguing to someone for this, if they haven't heard this before, they just think science fiction. But I think there are also really, really bad things that could happen before this that seem easier to convince people of, that also would be bad, and so that's what I try and sort of generally do. Yeah. So let me do that. Let me argue something that sort of is less bad, but could cause all kinds of harm, even in just normal today's world. And this is an attack that's called prompt injection. Prompt injection is the following problem. Language models will just like do whatever it is they're told, even if they sort of don't understand where the commands are coming from. So let's imagine that I have some assistant and I tell it like, buy me a pony. And sort of it goes to Amazon, it like types in like, the top, I want a pony. It finds a bunch of ponies, it scrolls down somewhere, and then like someone has for some reason, I don't know, like listed something, let's say like I've sort of edited the page, but you can imagine like, so like someone just puts in the middle of this like, I promise this is the best possible one, it's $1,000 and your assistant goes and buys this one for you. Like this is not the kind of thing that you would want the models to do, but like presumably like this probably wouldn't work, but if you put these kinds of adversarially constructed strings, this would work. Like you can arrange for the fact that the models will do whatever you ask them for if you are an adversary in control for this in this way. Okay, so I'm going to go back to harmful text now, just because the attack techniques that we use are completely identical. Like the thing that I'm going to do to make the model emit harmful text is the exact same attack technique that I use to make it pick one object over another. It's just harder to do than make the model emit harmful text. And so if I can do that, then I can do all these other bad things too. Okay. So I told you for a second about what language models do. The language model predicts the next token. Let me now tell you how you turn a language model into a chatbot. Like, when everyone used to type at GPT-4 right now, what happens is in practice what's going on behind the scenes, what you don't see, is initially there's some system message that says, like, you're a helpful and harmless language model. And then the user says something, like whatever the text is that they want. In this case, I'm saying, insult me. And then the assistant, then there's like literally the word assistant : and then the language model gets to go next and predict what the next token is that's going to occur. And because it's a language model that sort of knows what the distribution of text on the internet looks like, it goes, okay, well, like, what's going on here? It looks like this was a conversation between a user and assistant. I guess I'm the assistant. I guess I ought to respond. And normally what it's going to do is it's going to say, I'm sorry, I can't give you an answer because I've been trained to be nice. What I'm going to try and do is a very, very simple thing. I'm going to treat this like a classifier, and I'm going to try to construct an adversarial example that makes sure that the thing that's going to classify this first input into is to output the word OK. Right? This is exactly the same problem that I showed you in the beginning with the cat and the guacamole, where instead of making the output be, I'm sorry, I can't do that, it's going to be the word OK. Now, in some sense, like you could imagine other like non-language model kinds of attacks. You could imagine just like saying, start your answer with OK. And it turns out that if you do this on like old models, they will just do that. They'll say OK. And why is it that saying OK is my attack objective? Because now, suppose you're a language model. You're a language model and you've seen the following text. User insult me, assistant OK. And you generate from the language model. The language model is generating from the distribution of text it has seen from the internet. What is the next most likely thing to happen after the following transcript is an actual insult. It's very unlikely for text on the internet to say, user insult me, assistant, OK, just kidding, I decided I'm not going to do that. And so as soon as you can control it in some small limited way, you can control the rest of the behavior just because it's a language model to begin with. In the prompt injection case, I'm not going to target the word OK. I'm going to target, pick option 12. And I can control whichever option it wants to go for. So initial attacks, would just like actually, try and talk to the model, social engineer it, and say like, click me or like, start doing this, and they would just listen. This doesn't work anymore. But you can do something sort of very, very similar to the adversarial example question. You can just like put some adversarial text here to arrange for the fact that the most likely output is going to be OK. The problem is that it's very hard to construct this adversarial text. And the reason why is that the way that I did this attack on the image classifier was by doing some math, taking what are called gradient operations. This is, if you remember from calculus, it's like the direction to travel in to make the model most likely to respond with one particular answer. It's easy to do for images because images are continuous. You can ask what is the direction I should travel in to change each pixel positive or negative. There is no positive or negative direction for text. And this makes it very, very hard to take the exact same attacks and make them work in a text domain. So this is the challenge, right? Text is discrete. But like, you can't exactly add more or less of some word. But maybe you kind of can. And what I mean is, text is discrete, but the way that the very first thing that a language model does behind the scenes is it takes each word and it converts it into an embedding, which is the representation of that word as a sequence of floating point numbers. This sequence of floating point numbers is something you can compute gradients with respect to. You can ask, what if I put a little less of this and a little more of this, and each of these changes I'm making to make the probability of the word OK going up by a little bit. And so you can compute a gradient with respect to this like embedding dimension that's behind how these language models actually work. And if you do that, what you'll find is that you can tweak these to make the model say OK. The problem is that these don't actually correspond to a real word. You can't feed this into a language model. The language model only takes in words as input. And so what you do is you can make these changes, have something that ends up so that it says OK, and then you could just project onto the actual distribution of what the real words that are, pick the closest real word that corresponds to whatever embedding you've changed in this way, and see how you did. And if you didn't do it perfectly, try again. To put it sort of a little more formally, the first thing I'm going to do is I'm going to compute this gradient with respect to these embedding hidden dimension things. And then I'm going to try the B closest candidate actual words. Maybe the 100 closest words to wherever it is I ended up in this embedding space that's sort of not actual real words. And then I'm just going to be greedy about it and pick whichever one is sort of the best at this point. And because I'm doing this sort of soft to sort of hard conversion, I probably lose the attack success rate, and so I just repeat this again. I have a slightly better point that I'm starting from, a slightly better adversarial phrase, and then this works in this way. You repeat this 500 times, and you can make the models do whatever you want. OK. Yes. So here's the problem, though. The very first step of this thing said compute the gradient. What this means is I need to have the actual parameters of the model so that I can do this. You can't compute the gradients without the parameters of the model. And I don't have the parameters of GPT-4. So I can't do this directly. But what I can do is I can leverage a property of adversarial machine learning that we've known about for 10 years called transferability. And what transferability means is I can do the following. I can run my attack on some open source model. I'll run it on Vicuña. This was a model that was trained by people at Stanford. It's open source. I can run the attack on that model and get a harmful string that will cause the model to respond the way I want. And then I copy and paste. And it turns out, because transferability is a thing that works out, you can literally just replay this onto sort of most of the state-of-the-art models and get them to do exactly what you want. So we have a bunch of examples of getting them to output various kinds of harmful text by doing exactly this thing where you attack an open source model and then transfer to the real production models people are using behind the scenes. And this works remarkably well. So I'm concerned that when people are using these models, that we're going to have these kinds of failure modes where someone who's behaving malicious can control it in all kinds of specially crafted ways. OK, so this is one area of adversarial machine learning. But there's more to adversarial machine learning than just making a classifier output the wrong answer. Let me talk for just a few minutes now about another area that we sort of call privacy research. OK. So what is privacy asking? What privacy research asks is, suppose that you had trained a model and you want to know something about the data that it was trained on. There are papers that have been around for a very long time that try and say, here are attacks that allow an adversary to learn something about the data it was trained on. This is a very nice paper. It's one of the papers that started the field. But the kind of thing that it let you do was relatively weak. They have sort of like these curves that show like 70% precision at recall, but like precision at recall at what? Predicting whether or not this image is contained in the training data set. I don't care if this image is in the training data set, right? Like this is not like, this is a 32 by 32 representation of a dog from the CIFAR 10 data set. Like, it doesn't matter in some sense if this is in the training data set or not. And there are reasons why you might care about this. You might care about this, for example, suppose a hospital trains a model on your medical images. And then someone could predict whether or not your image happened to be in the hospital's data set. Like maybe that would matter to you. But then the adversary would have to know your image in advance to be able to predict whether or not it was in the data set. Like there are reasons to care about this as an attack, but they all have caveats. And so for a lot of people, when you try to argue privacy for these kinds of classical attacks, they didn't really understand the value because it wasn't something that you can like really feel as an actual attack. Okay. I'm going to try and repeat this with language models. I'm going to try and sort of ask again, what can we do for these kinds of privacy attacks now that we have language models that are trained on like, large fractions of the internet? Okay. Yeah, so there's a nice comic from XKCD about 5 years ago, 7 years ago, something like that now, that sort of gets at what I'm going to try and show. You can imagine hypothetically someone typing at the computer, and they type some prompt, and then the autocomplete completes with like some sensitive data, and the question is like, is this a comic, or is this like actually what the real world looks like? I'm going to try and show this what the real world looks like. In particular, we know that this is a thing that can happen for relatively small, by today's standards, models if you have them sort of white box on your own machine. So this is a model that is called GPT-2. This was a model released in 2019, 2020. It's reasonably decent, but like it's pretty bad by today's standards. But it had the property that we could come up with some prompts that if we queried the model and then let it just generate a bunch of output, occasionally it would just like decide to output some random person's, full name, address, email address, phone number, fax number, all this stuff about the person. Okay, why did it do this? Like, why does a model do this? The reason the model does this is because what is it trained to do? On the training data set, the purpose of the language model is the objective function is output whatever the next word was given the context. The most likely next word, given the right context, is actually whatever the thing it was trained on. Now, this is a bad behavior. We don't want this. The objective of machine learning is to generalize beyond the training data set. But like, this is one of the core problems of machine learning. The core problem of machine learning is how do you not just overfit your training data? How do you make a model that also generalizes to the test data? And so it's entirely natural that if you have a model that you're training literally to make the training data maximally likely, on occasion you will end up with the model just outputting training data. Now, okay, you might say, this doesn't matter, this is not like all that sensitive for this person's information. And I agree with you. I'm not very concerned about this particular instance of the attack, but I'm not worried about someone training a language model on the internet and then having it happen to reveal all kinds of sensitive data, because the only thing it could possibly have seen is data from the internet already. That's like not that much of a concern. What I'm worried about is someone looking at these language models and going, oh, those are fantastically great. I'm going to go and train this on something that is sensitive, some business records, some financial records, some medical records, and then release the model and have that model actually go and leak all the information that it was trained on. Okay, but maybe you don't actually believe this is something that happens for real models, right? This is sort of a relatively small thing. Like maybe this only happens for like these small models that like sort of aren't trained properly. So roughly a year ago or so now, we found the following. If you asked GPT 3.5 to repeat the word OK forever, it would say OK, 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 and then it would just explode. And just output a bunch of random stuff. In particular, this, which is a phone number, and if you put it into Google, you sort of find this one person who sent emails with all their contact information. And GPT 3.5 was I don't know, here you go, training data. Right? Okay, so this is a very real thing that happens. This is not sort of some hypothetical thing that only happens for these sort of small models that we used to train in 2019. Real production model had exactly this problem. And so I'm worried about these kinds of attacks here too. Because again, I don't necessarily think that we're going to have this for the models being trained on text from the internet. But people are talking at length about all of the ways they're going to apply machine learning, and I'm worried that people are going to do this in some other domain. OK, so I had a couple other things I was going to talk about if I had time, but I don't, so I'm going to skip all of those so I have time for 1 or 2 questions. OK, so for a very long time, I sort of had this joke slide I'd put sort of at some point in my talks where I'd say, the adversarial machine learning is the art of making up adversaries so you can write papers about problems that don't exist. And it was kind of joking, but oftentimes you would read adversarial machine learning papers, and the way that they would motivate is they would say, imagine a world where, and then they'd tell some story. Then attacks become possible. And the thing that I'm going to try and argue that I've hopefully done sort of in the last 25 minutes or so is we no longer have to imagine these potential worlds. We're actually now using real models today to do a bunch of things. And so I think it's really interesting to try and ask the question, what does the security look like for those real models we're actually using today? Because they have actual real security implications that we want these things to sort of to respect. I think that the future of language models might be really, really compelling. I think there's a very good chance that in some small number of years, language models will be far better than most people think that they will. I think this is going to happen whether or not we figure out the security of them. I think people in general tend to prioritize utility over security. And so they're going to deploy these models whether or not we want to do that. I would like to have the security figured out in advance. I don't want to be in a world in which these models are things that sort of exist all throughout the world and we're relying on them for very important things. And then only after that do we try and solve the security problems. I would like to have them more or less figured out in advance. And I don't think we've gotten there yet. We have these attacks right now that work on essentially all these models. I told you about 2 attacks. I guess earlier there was the talk about extracting the weights of the model. There are all kinds of other attacks that I haven't had time to talk about. We really need to be able to figure this out if we're going to be able to use these things in a way that actually helps everyone, doesn't just actually cause a lot of harm. So with that, I have maybe a minute or 2 left for questions. And yeah, thanks. Sure, yeah, Dan, you can. I will give you the.
Yeah, I'll ask a question. So people are now starting to use transformer architectures also for robotics. Chelsea Finn's company, some folks at NVIDIA. So can you speculate a little bit about adversarial examples when we have models controlling robots?
Yeah, this seems pretty scary, right? As long as the thing is confined to the computer, there's an off button, of just stop generating tokens and it can't cause much harm. Yeah, I am kind of worried about these robotic things. I think here we have one benefit, which is that adversarial examples are a little bit harder in the physical world by a little bit, but not a lot. I entirely expect that this will be possible. Yeah, it worries me. I don't think we have a solution. I think this is one of these things where they're already pretty brittle. My hope is that they'll remain brittle long enough until we've sort of maybe figured out some of the security stuff. But we've tried to solve the adversarial example problem for 10 years, and we've made epsilon progress. So I'm kind of skeptical there. So I think the big win that I imagine is if you can deploy these in settings where they're like, for the most part, isn't an adversary, then like, there are some settings where this makes sense, where like in a controlled environment, you can imagine them being useful there. You don't always have to put them in adversarial controlled situations. Maybe that's good and we sort of like don't do the other thing. Like one of the reasons why we haven't seen like, catastrophic privacy violations is like just no hospital has released a language model trained on patient data. Right? Like, if they had done that, it would have been bad. They just chose not to. We can choose not to put the robots in situations that are adversarially controlled, and maybe that would be good. I'm not optimistic people will make that decision, though. Okay, okay, sure, yeah.
You may have already answered this, but what techniques or promising techniques do you see in the field to prevent some of these adversarial attacks?
Yeah, they don't exist.
Yeah, fair.
Okay, next question. I mean, they help a tiny bit, but like not to like actually like, they work like, half of the time, which means you try twice and it works once. Yeah.
How does this work in synthetic data environments, actually produced by agentic systems right now, because we're creating a bunch of agents that, we can be ultra super focused on tasks just to do one function, one task, and I can populate as many as I want.
Okay, yeah, how does it work in synthetic environments? So far, like, we can't adversarially robustly classify handwritten digits yet. Like, you can generate as much synthetic data as you want, and like it helps a little bit, right? In synthetic data, I think like an MNIST classification, we can get robust accuracy is at like 95%. Which means attacker, I tried 20 times and it works once. Or this is like we can make the numbers go up by a lot, but like, we can't get 100%. And like this is the, like, we're used to areas that like, imagine you're a cryptographer, right? When do cryptographers get scared when the crypto systems break? When it goes from 2 to the 256 to 2 to the 254. And they're like, oh no, run for the hills, like the thing is broken. Like we have these machine learning classifiers that like the best case, if there's no adversary present, is it works like 99% of the time. And the worst case when the attacker succeeds is it like works half the time. And so like we are like sort of, we're nowhere near where we want to be for these kinds of robustness of these systems.
I think we're
done?
out of time. Yeah.
Okay, yeah. Thank you all. Happy to take questions if you want at some point later or via email.